everybody. I'm coming from Berlin, where it's as hot as in Paris, maybe 2 degrees less. I work at SoundCloud as a payments engineer, and I organize Elm Code Night, and I co-organize Elm Bridge in Berlin. So this talk is about a pet project of mine, Elm Physics, and it's called Fighting the Laws of Physics with Elm. And the word fighting there is it represents my struggling with computational physics, because I have no prior experience in this topic. So when starting a project like this, there are many challenges that you might be facing. So you might want to know, you don't know ahead of time whether this will succeed or not, whether your project will work, or will it be performant enough or not, or is your choice of language right? Have you made the right choice of language? And at some point, you're pretty frustrated because you don't see the results immediately, and you might want to just stop the world and flip the table. That's me. Yeah, so basically my talk is, I will try to flip this imaginary table for you so that it will demystify some of the concerns that you may be having when building something complex. So how do you build complex things? By first building simpler things. And this is my path towards eventually making a physics engine a thing. I first started with a simple Tetris game, and I used it to learn Elm. Then I built a couple more games that used WebGL, so I learned about WebGL, and I wanted to do something in 3D. And that's how I built a Rubik's Cube game that allowed you to interact with a 3D object. And not so long time after that, there was a game jam, and the topic of a game jam was to build a game about randomness. So I took a challenge and I built physically simulated dice. And you can see that it was successful. But in order to make it work, I spent about 2 months building the physics engine, and then just 2 hours to put this demo together. So this is how Elm Physics was born, and the way I started with no prior knowledge, I was looking into JavaScript implementations, mainly Canon.js, and then I just tried to understand the code, because I'm not good at reading research papers. So this is how the main module of Elm Physics looks like. It is built around type world. So empty gives you an empty world that doesn't have anything, and then you can add bodies to the world. So you can read this from the function signature. It takes the body, takes the world, and then gives you back the world with that body in it. And then the main thing is the main logic is in the simulate function. It takes a number of milliseconds since the previous frame. It takes the current state of the world and it gives you a new immutable world after this time has elapsed. And then when you want to render this, you use getBodies function that gives you back the list of bodies from the world. So you can render it with WebGL. So Elm Physics is not focused on rendering, it's focused on physical simulations, and rendering should be done separately. Another main, and the second most important module is body, and it lets you create bodies of different shapes. So you can create a box, a plane, and a sphere. And you may wonder why there is data as an additional type parameter. And data lets you attach any arbitrary information to your bodies in the world. So in the simplest case, it could be its visual representation, a mesh that you can use to render with WebGL. Or if you want to make something more complex, then you can attach a user-generated ID, and then you can link any external information from your Elm program. This module also exposes a lot of functions that can help you working with bodies. So you can set mass. By default, body is of 0 mass, and it means it cannot move. So you can set mass, you can rotate, change position, change materials, and materials allow to control bounciness and friction of bodies. And there are some getters, like get transformation and get data. Those are helpful for rendering. So you can retrieve the mesh, and you can get the transformation, which is a concatenation of rotation and orientation and position in one matrix. So how does it work internally? There are a few stages, and the first one is called broad phase, and its responsibility is to give you pairs of bodies that can possibly collide. Then the narrow phase is actually colliding those bodies, and it gives you a list of contact points. And then the main brain of physics is the solver, and solver takes all the constraints enforced by collisions, and it calculates updated velocities. And then all you have to do, you take the time since the previous frame, you take velocities, and you calculate updated new positions and orientations of all the bodies in the scene. But maybe some of you are still skeptical about, like, why doing this in Elm? So my reasons why are that because I can build some fun games and demos. And those demos are of very small size. So if you want to put something like this using Three.js and Canon.js, then the overall JavaScript bundle is 10 times more than doing it in Elm. Of course, you get a lot of extra functionality from those libraries, but you may not really need them. Another reasons include research and education and sharing results. When you think of using immutable data structures and pure functions for physics, you can get things like time traveling. And it comes at no extra cost. What you can do is you run the simulation, and then you keep a list of previous states, and it captures the whole physical world with all positions, orientations, velocities, so that lets you replay it from any given point in time. If you want to do it with mutable way of programming, with object-oriented programming, you would have to write serializer and deserializer to capture that state. And the last reason is sharing results. So actually, Evan was presenting last year at this very stage, and he defined success for the community. He said that one of the important aspects of a healthy community is an emphasis on sharing results. And by result, he means that the result is a concrete outcome. And by the way, his slides featured the dice that I implemented. So, and that's partially why I'm here. I'm sharing my results with you. So what were the challenges? There were 3 challenges. The first one, migration from Canon.js that was written in terms of object-oriented programming. Then it was troubleshooting and performance. Canon.js code is really nice. I'm really helpful it exists because I could read the JavaScript and then port it to Elm. But there are a lot of differences between object-oriented programming and functional programming. So in object-oriented programming, you have complex class hierarchies, and what I mean by that is, if you have like a base class that defines certain methods, and then you have another class that inherits them and then replaces some of the methods with different implementations. So when you want to port it to functional style, you have to traverse this class hierarchy in order to figure out what is actually being called. And in Elm, we focus on execution, so we can use custom types to represent different things, and then we have explicit pattern matching what should happen in all the cases. Also, in object-oriented, we have methods that are coupled with data. So imagine one object is called, you call a method on one object and you pass another object to it, and then in that method you call another method on that other object, and then both of them are mutated, so you don't really know what's going on. In Elm, you have functions, and you know what is the input to the function, what is the output that is coming from the function. Also, object-oriented programming has sort of implicit execution order because you can imagine it as a self-organizing net where like it becomes a living organism, sort of. And in functional programming, you have explicit execution order, so you can see and read it from your program. The way functions are called, and you can imagine it as a system of pipes. Troubleshooting was a really hard problem to me because of my lack of knowledge of computational physics, so I could only, reading from JavaScript, I can only tell whether things are behaving correctly or not. And when I implemented the very first demo, the box fell down, and once it touched the ground, the coordinates exploded and it just went into the space. So, and then I had to figure out where exactly things went wrong. And I could not avoid not using dev tools like a JavaScript debugger to figure out what are the values that are different from Canon.js, and then I walked up and tried to figure out where things went wrong. Tests were really helpful, and it's good that Canon.js had tests, so I could port some of them to Elm and then work towards them passing. And the last most helpful thing was visual debugging. So with tests, with unit tests, it's really hard to capture all possible states because like you have all the ways to collide two bodies together, and it's you cannot even enumerate all possibilities. And for that, I built a very nice demo setup within the project. So you can toggle wireframes, you can see what are the collision points, or you could add some extra buttons like this, so it drops random shapes. You can also see normals to the surfaces and check the FPS. Speaking of FPS, the number of bugs, sorry, the categories of bugs, I could classify them into three. I think I was like super lazy when developing with Elm, so I was not really paying attention to anything because of type system. But there are some sort of errors that Elm cannot capture. Mainly, if you have a function that takes the arguments of the function of the same type, then you can mix them up. And a lot of the errors were caused by wrong order in vector subtraction, because sometimes I would pipe through vector.subtract, and you would think of it as you would, like if you pipe A to vector subtract B, you would think that B will be subtracted from A, but it's the opposite. Another thing is I was focusing on performance, so I didn't want to use list.map, and I was always using fold, and fold actually reverses the list. And if you have a list of vertices on the surface of the face and you want to calculate normal, then the order, the winding matters. So if you reverse that list, then the normal will be facing in the opposite direction. And the last one is run algorithms, and this is something due to my lack of knowledge in like what is going on in the code. So performance. What was really helpful with performance is setting up the following demo, so I could easily measure the progress by looking at this. And I used the browser profiler, and then I could determine which part of the execution is slow, and then I could use Elm benchmark to actually squeeze the best performance out of that bit. So these are the improvements that I made. Apparently, record-based linear algebra performs faster than the one that is based on typed arrays. Also minimized array usage, so especially when you want to iterate, it's better to use list than array, because you would have to call array.get, and it's way slower. I also inline vector operations. So if you chain multiple operations, like you take vector, then you add another vector, then you scale it, every time you call it, it would allocate another vector. So you can do it per x, y, and z, which are just float values, and that would not allocate extra memory. And I use tail-optimized recursion. So if you're curious, you can check the JavaScript code that has been generated, and it is a while loop. So it's not actually calling the function many times. So it's a while loop with many local variables. So speaking of the future, I want to build more games and demos. They are great because they also drive the API, so I can figure out what's the best way to have pure API in Elm. I would like to improve the stability, because if you look at this, it's constantly being evaluated, and sometimes boxes move slightly, so I want to be able to for the scene to stay stable. I would like to expose collision events that are very important for games, and I want to be able to apply forces. So for example, in this demo, I have to drop the car on a slope because there is currently no way to have a motor for that car. And as for the rendering, there are good news. Ian is working on a high-level 3D rendering engine for Elm. So you will have physically based rendering, and you can use it with physically simulated world. And it's coming soon because he has committed to present his work this September at ElmConf. There are some links. I'm going to share the slides with you. So please check my posts on Discord. There is much more information than I'm able to present in 20 minutes. And check my games. Follow me on Twitter. And I would like to thank Ian McKinsey and Matthew Griffith for helping me with developing a nice API for Elm Physics. I would like to say thanks to the creator of CanonJS. I would like to say thanks to Paul Martel, who contributed more tests, and he implemented spheres for Elm Physics. And I want to thank for all folks from the Elm community who have been encouraging me to work on this project, and especially folks from the game dev channel. And that's it. I hope that you can try and use this library and build something that is more colorful than my slides. Thank you.
Thank you so much, Andrey. Yes. Thank you. Okay. Okay, we'll do. Yeah. Do you have any questions? Do you want questions?
Hi, thanks for the talk, so it's great. So I have built a game before, and I had found that one of the most complex thing I had was dealing with multiple physics thing that could happen between two increment phase. Like, for example, I will have a ball that will hit a wall and another ball that will come in the same area, and how I can like deal with all those events at the same time and have a coherent result after the ticking. So how do you deal with those kind of things?
I think that like the velocities in the world and the movements, they have to be in such a way that there is an overlap for a moment, like there are frames where bodies would overlap, and then this would create a collision point, and then you have some sort of repulsion and they're going apart. So it's so the way it works is sort of the way I kind of described in the in here is that, so you take like a snapshot, you see things that are touching together, and this sort of creates some kind of repulsion. Like each contact point creates a constraint to separate those bodies, and then like it calculates all the forces, and then things are moving apart to not really overlap.
Okay, so you apply all the forces at once and not one after each other. Okay.
Andrey, did you say that mass zero are the immovable masses?
Yeah, and it's a hack. So it's actually infinite mass, but
exactly.
This is how it's represented.
I see. Okay.
I'm wondering if you think it would be eventually possible to like import like more complex bodies from like 3D modeling software or something like that, or if you just have to write them all in Elm.
So the way boxes are currently represented is in a very generic form as a convex polyhedron. So it's like a list of faces, and each face is defined by its vertices. It's just that this API is not exposed because just to make impossible states impossible. So if I can somehow figure out what the API could be, so that you cannot construct impossible shapes, then it would be possible to have something else other than boxes.
Cool.
Hi, do you support particle systems or deformations?
No, so it's like a rigid body, so you don't have deformations. And for particle systems, there is an open issue to add a particle as a body, and I think the way it's done, it should be done as just like a sphere that has no radius. So about systems, I'm not sure what it means. What is a particle system?
Well, for example, like simulating smoke or something like that. Explosion. Yeah.
So like it's spawning multiple particles with different velocities. I think it could be possible if I introduce a particle body. Okay, I think no more questions.
Sorry, could you tell us a little bit about how does the performance scale up? Like, is it based on the number of bodies, or is it the complexity of bodies, and is it linear, or?
So the performance. So when I was looking at the performance, and everybody was telling me that the collisions are the most important thing, and actually it was not the bottleneck. So I didn't have to do something like spatial indexing. The current broad face is basically checking every two bodies together, so it's n square, and then it uses bounding sphere radiuses to do a very fast, very quick check, and then actually perform the calculation of intersections. But the solver part is depending on the number of contact points in the world. And so it depends on how many contacts are, and then every contact is transformed into two friction equations and one contact equation. So there are three equations per each, and then all of them are passed in the solver and update information that is stored in the body.
So you can have any number of objects you want as long as they don't touch each other.
Yeah, or if you have a bunch of spheres, because sphere, when it goes over the floor, it only has 1 point that is touching. So if it's a box, you already have 4.
And I assume points, unlike a box, are just the vertices. You don't actually have infinite numbers of points on a sphere. Right? Okay.
Okay. So you did it. Amazing. Thank you very much.